All right, let's get started today. The hope is to finish up the chapter today. Maybe not, but this whole chapter is on electromagnetic waves, right? But we haven't really even talked about anything wavy yet, right? We talk about electric field and we talk about magnetic fields and how they're connected to each other, right? And depending on which frame of reference you're talking about, you can actually basically observe a magnetic field, right, where there's only an electric field and a different frame of reference, or you can observe a electric field just by moving relative to a another frame of reference that has a magnetic field, right? So this was this thing we were playing around with yesterday. And so, the one interesting thing that came up with in this discussion also is that these constant epsilon naught and mu naught, right? If you take, 1 over them and square root them, it turns into the speed of light, right? And then we'll see how that's gonna play out in a second, okay? I think we're trying to keep the mystery so far, okay? And so we're gonna just talk about like all the stuff we learned about electricity and magnetism so far, right? This big review thing, right? So back in, I don't even remember, chapter 23, right? Right in the beginning of the semester, right? We learn about this thing called Gauss's law, right? What Gauss's law tells us is that if you have some Gaussian surface, right, and you know how much charge is inside, you can actually figure out what the electric field is, right? Actually, technically, what's the flux, right? Right, is E dot dA, which is the electric flux through this surface, right? Right. Remember the original experiment was that, if I have some box and I don't tell you what's inside, right, and there's some electric field coming out of it, right away you can tell me there's some positive charge inside, right. And if the electric field is going inward, we know there's some negative charge. If there's no flux, right, then there's actually no net charge inside. Okay, so this is known as Gauss's law, right? So way back when we were messing around with this. There's also a magnetic version of it. It's not as interesting because what happened is that this magnetic flux always comes out to be zero. Okay, E dot dA tells you how much charge is inside a little container, but B dot dA tells you how much magnetic charge there is. The problem with magnetic charge, there's never a single, just a north charge by itself. We have never been able to see just a north. You've never been able to make a magnet that only has a north pole, right? Or a south pole. They always have both, so they actually kind of basically the poles negate each other. And therefore, right, what happened is that the magnetic version of Gauss's law basically always come out to be zero. And you can use this to do some calculations also, right? The flux is always zero. The magnetic flux is always zero at coming out of an enclosed surface, right? All of this only happens if you can enclose all of these magnets, right? Thing we learned, when was this? This was a couple of chapters ago. We learned about Faraday's law, right? Faraday's law has to do with magnetic fields that are changing, right? If I start moving this thing around, it can actually create an electric field or current or voltage, right? And light up this light bulb just by moving a magnet around, right? And this is how like a power generator works, how a windmill works, how, just by moving things around, changing magnetic field gives you electric field somehow, right? And this is Faraday's law. Faraday, like what he found, okay? And then the equation is that, well, some changing magnetic flux with a negative sign in front, right, tells you how much electric field is generated in some sort of current loop, right? So E dot ds, this is a line integral, right? So when you do line integral, you're integrating over some wire, right? But when you're doing a surface integral, you're integrating over some sort of sphere or surface or box, right? The thing we learned most recently is also Ampere's law. Ampere's law tells you that, well, it's very similar to Faraday's law, where the left-hand side is also going to be some field dotted with some line integral here, right? Dot ds, right, instead of dA. So that means it's the magnetic field dot producted along the line of the wire, right? And we can actually figure out that, well, that tells you how much current is actually inside that loop. So for example here, if we have a current going upward like this, I can draw an Amperian loop, right, like this, right? And we can figure out how much what is the magnetic field, some radius r out here, right, just by knowing how much current is flowing through that loop, right? Does this all sound familiar, right? A little bit, maybe, right? So I'm going to bring up one more little side note before we move on to actually showing you what electromagnetic waves are, right? So there's something odd about this where, right, the that was not what I meant to do, right? Faraday's law, or the electric field version of the line integral complicated thing that we have to do, right, has to do with a changing magnetic flux, right? Right? Ampere's law, which is very similar, right? I'm even going to highlight the same thing, right? It's B dot ds instead of E dot ds. Looks very similar. You would think there'll be some sort of changing electric field over time here also, right? Because I told you that, well, electric field, magnetic field, they're all basically the same thing. It just depends on your point of view, actually, what you see, right? So there's something wonky going on here. The right-hand side doesn't make sense, okay? And this is where we're going to have this discussion about displacement current, okay? So displacement current is a current that's apparently that can happen even though there aren't charges moving around, okay? And we're going to showcase this by having a alternating current circuit. So this is why I think like covering chapter 32 is actually useful before covering chapter 31, okay? Where you have some alternating current, right? So what's happening is that, right, as the voltage on this side goes up, you get some positive charge here, right? So if I plot, let's say voltage versus time here, right, it goes up and down, right? So when the voltage is positive here, it's going to make some positive charge here. When the voltage is negative here, it's actually going to flip this, right? It's just flipping back and forth between the capacitor, right? And I've been telling you that that allows you to transfer current over the capacitor, right? Remember, on a DC circuit, the current cannot hop over that capacitor, right? Only in an AC circuit, you can have this oscillation. I'm not sure how to do this, right? Up and down charge, right? That allows current to actually pass through. But I never told you what's actually going through it. It's not electron, right? It's weird, right? So how are electrons being able to jump this gap, right? It's not doing that, okay? So what we're going to do is we're going to think about zoom into this little circuit here where we have some AC source, and then somehow we're able to drive current through a capacitor, right, with an alternating current source, okay? So we're going to look into this little thing more detailedly, okay? So this more detailed drawing of our little capacitor with a battery hooked up to it. What happened is that the current is the actual electrons, right? Actually, the electrons are going backward, right? But imagine just a bunch of plus charges, right? It arrives here, right, and gets stuck here, okay? That makes sense, right? We have some current going through here, and we can actually reach this side, right? But it can never jump over this gap, right? Right? What happened is that if you have an alternating source here instead, let's say it replaces battery with some function generator, or just plug it into your wall here, right? Now this thing is going to go up and down, up and down. The amount of charge here is going to go positive, negative, positive, negative, positive, negative, right? What's between these two parallel plates when you have charges on the plates? Before I go down there, electric field, right? Right. There's also a magnetic field, but we're going to see how that actually gets generated. Okay. So there's an electric field between these two plates, right? Right. So, but this electric field is no longer constant, right? Because you're making this plate very positive and then going very negative, going very positive. So this electric field is also increasing, decreasing. It actually goes negative, right? Right. So this electric field is going positive at one point, right? Going back to 0, and then going negative, and then going back to 0 and positive. So this is a changing electric field, right? Right? And hopefully that's gonna remind you of what we can plug into the end of Ampere's law in order for us to have a complete picture actually what's going on when we have alternating current in our system. Okay, so the current is actually carried through empty space using electric fields. Okay, it's actually not the physical charges that are hopping over. It's actually this energy is transferred over by just electric field that's being generated on this side and transferring over here, and then what happened is that when the voltage flips, right, basically the positive charge lines up here, the negative charge lines up here, and then the changing electric field is actually what's transferring the current over. Okay, so this is not a real electron moving around current, so we're going to call that displacement current. Okay, so it's a special name. It's not technically charges moving, but essentially what it does is it transfers that energy over the capacitor just the same. Okay, and this displacement current, as we saw up here, is going to have something to do with electric fields, right? Or actually has something to do with changing electric fields. Okay, in fact, the displacement current is actually the derivative of the electric flux, meaning basically whatever the electric field is in here, right, multiply by the surface area of the capacitor plates, right? That's the flux, right? How much that flux is changing, it's going to tell you how much displacement current you're going to get, okay? And this constant here, epsilon naught, is just so you can convert the units correctly. So you have, because right here you have basically the units for electric field times an area divided by time, right? And then on the left-hand side here, you have the units for charge per second, right? That's what a current is. And this epsilon naught actually allows you to convert the two units. So they are going to be the same, okay? So what we need to do is actually modify Ampere's law, okay? Ampere's law only has this little piece here. What we're going to do is add this displacement current piece to it. And this is going to be the complete set of equations that we can use to actually do all of electricity and magnetism with, and this is known as the Ampere-Maxwell law, because Maxwell is the one that figured out this piece. Okay. Okay. So adding this little piece to it, right? If we go all the way back up to our original equation up here, that didn't make sense, right? This little piece here, if we added this little piece to it, right, d flux by dt, now these equations make sense, right? Because now basically what you should think about is that a changing magnetic field, or just actually changing magnetic flux, gives you electric field. A changing electric flux gives you a magnetic field, right? The two actually makes each other, okay? And it's going to go into what light turns out to be. Okay, any questions about this before I do an example? You guys believe me? Maybe? Which one? This one? Yeah. Yeah, we're going to do an example with this real quick, okay? So let's say, right, we have a 2 centimeter diameter parallel plate capacitor with a 1 millimeter spacing between the two, and it's being charged up, meaning there's going to be a change, right, in how much charge there is. That means there's going to be a change in how much electric field is there, okay? It's being charged up at the rate of half a coulomb per second, right? What is the magnetic field strength inside the capacitor at a 0.5 centimeter away from the axis? Okay, this is kind of a difficult problem, and this has to do exactly with what we just learned so far. Okay, so to set up the problem, we want to make a little drawing as usual. Right, we have some parallel plates. Since we gave us diameter, so we assume that these are circular shape. Right, I'm trying to draw these two capacitors. Right, so this is like the positive side, this is the negative side, right? And what's happening is that there's charges, positive charge piling up here, right? And that means negative charge is going to pile up on the other side here, the same amount. I'm going to draw 6 also. But it's going to be changing, right? We're adding more charges every second. Okay. The electric field between the two is going to point this way for now, right? Okay. So in order to figure out how to deal with this is that let's write down what the Ampere-Maxwell law is real quick. Okay, I'm going to copy that down. So this is this B dot ds, right? Some sort of magnetic field equation is basically going to be equal to mu naught times whatever the amount of current that's going through our loop plus epsilon naught times how fast the electric field flux is changing. Okay? Okay. And what they want to determine, oops, I'll go back up here, right? The radius of these things, the diameter, right, is 2 centimeters. That means the radius is actually 1 centimeter, right? And want to figure out between these two guys, what color works here? All right, I'm just trying to do this, okay? Between these two guys, right, at some radius, actually this should probably be a big R, at some radius little r, right, of half a centimeter, right, what is the magnetic field here? Okay, kind of a complicated drawing. Okay, all right, so now we can apply the Ampere Maxwell equation. Okay, so the left hand side, if we have this little loop here, right, this is where our B dot ds is happening over. Let me just color code that with green or with orange also, right? Okay, so the B dot ds is happening over here, right? Since this is a circularly symmetric system, we can assume that the magnetic field is constant on that circle, right, as we usually do. So therefore, we can actually bring it out of the integral. If we bring it out of the integral, we just get b, right, the integral of ds, right, which is basically the length of that circle, right? The length of a circle is the circumference of a circle, right? And then the dot product is going to give us a factor of cosine of 0 or equal to 1 because, right, the magnetic field is going to be going this way, and then ds is also going to be this way. They're always parallel to each other. Okay, so this is going to be b times 2 pi times little r, right? That's the circumference of a circle. Remember, right? Okay, so that dealt with the left-hand side. The right-hand side, right, since we are in space, the space between the two things, we should have no actual electron that's moving, right? There's no actual charge that's moving through. It's actually the changing electric field that's creating this displacement current. So this piece is 0. Okay. Over here we have mu naught times epsilon naught, if I factor this in. Now all we have to do is try to figure out, let me color code things. So the stuff that has to do with electric field is going to be in blue. Now we have to figure out what is the changing electric flux between those two capacitor plates, right? Okay. Okay. Since we have a constant area across this, right, this is just going to be whatever the electric field is, right, as a function of time. Oops, forgot the derivative, don't forget that. The electric field is as a function of time times the area between the area around this little loop, right? So instead of the circumference, it's the area, so that's actually pi r squared, right? That's the area of a circle, okay? And since these are both constants with respect to time, the only thing that depends on time is the electric field, right? Okay, in fact, we can start canceling terms here. We can cancel out this guy, next guy, cancel out this guy, cancel out one factor of r, okay? And then what we have next is going to have mu naught, epsilon naught, right? And then the r can be pulled outside because it's constant with respect to time. I have to figure out how fast is this electric field changing with time. Okay? Okay. Right? And remember the electric field between two capacitors. This is gonna, remember how to calculate that? It's relative to the charge, right? It's the surface density divided by epsilon naught. Remember, right? The electric field between two capacitors. Right. This is where I have to go back to our, what chapter was that in? Should have looked this up beforehand. When we did capacitors, is that 27? Yeah. Capacitor. Yeah, this is where we cover capacitors. Do the energy density. Let's go up, go up. Anyone remember that equation? Is it divided by epsilon naught? I think it is. I just want to make sure we got the constant right. And so we have batteries. Come on. Right, here's one. It's the charge. Yeah, it's the charge over the area, which is the charge density. Yeah, divided by epsilon naught. Okay, so I did get that constant right. Now I have to go back to my chapter, which is this one. Okay. So the electric field, right, is going to be whatever the charge density is, which is the charge divided by the area of the capacitor plate divided by epsilon naught. Okay. Right. So therefore, we can plug this in here. Mu naught epsilon naught r. Still a time derivative we have to deal with. Charge. The area of that capacitor is actually pi big R square. Well, big R square, right? Because that's the whole area of the capacitor plate, right? Not the area of the little Amperian loop we drew. Okay. There's an epsilon naught here also. We can start canceling a few terms, right? And then the R is actually also constant, so it can go out here. Ooh, my marker disappeared. Right? And now what we end up with is mu naught little r big R squared. There's a pi on the bottom, right? And then how fast the charge is changing. And they told us this thing, right? This is 0.5 coulomb per second. Okay? So with this, you can actually plug in everything. So the left-hand side is actually 2 times B still, right? So the B field is actually this quantity divided by 2. Okay? So let's calculate what that is. Okay. What's mu naught? Mu naught is 8.85. No, that's epsilon naught. Mu naught is the 4 pi times 10 to the 2, right? Sorry, times 10 to the 12. Is that right? Mu naught? Should I look that up? Permittivity of free space. That's what it's called. Permissivity of free space. Which one is this one? That's epsilon naught. Not very useful. Vacuum permittivity. I looked up permissivity. I think Google corrected. Permeability of free space. That's a weird number. 10 to the 10 to the 7. Yeah, I think that's what that is. Negative 7. Okay, now I need to go back to my calculator. Negative 7. Okay, times r. That's the little r. Right, that's 0.005 meter. Right, 5 centimeter, half a centimeter. okay, times how much the charge is changing, is just half, divided by pi. Well, I guess we could have took out that pi, divided by 0.011 centimeter squared, and then all of that divided by 2. Okay, so the magnetic field is going to be 5.00 times 10 to the negative 6, and since we all use what is it called? SI units, it should come out in Tesla. Right? So this is sort of a complicated way to figure out how to use now this modified version of Ampere's law. Okay? Any questions about this? Okay, besides looking up constant, it wasn't too bad, I think. Yeah, question? The electric flux, right? So the electric flux, remember when we talk about, flux over a surface, right? Some electric field going through here, right? If you have a constant electric field, or actually a constant area, right? The flux is just going to be the electric field times the area dotted with the area of that, right? So what happened is that I modified this to the electric field times the area of the little Amperian, the orange circle in the middle there, right? That's the amount of flux that's going through this little area down here. Okay, so that's where that went. Okay, all right. So just to kind of like do another review. So these are the combination of all these equations. All four of these guys together, right? They're known as Maxwell's equations. Right, we have Gauss's law, we have Gauss's law for magnetism, we have Faraday's law, and now we have completed this Ampere-Maxwell's law where we added this changing electric flux thing also, right? And this plus, the force law, meaning how much force if you put a charge Q at some electric field E, right? That gives you, right, what is the force, the electric force on something, right? But let's say that charge is moving in a magnetic field, right? That also gives you the magnetic force, right? So the addition of these two forces are known as the Lorentz force laws. Okay, that tells you exactly how much force will be applied to a particular charge if it was moving in either an electric field or a magnetic field. So all of this is all you need to do like 99% of like everything in this world. Yeah, Alex? Oh, this is velocity speed. Yeah, this is the velocity vector. Okay. Okay. And this is kind of cool because like with these 5 equations, basically like all of our computers, all the lights, all of modern society works because of these 5 equations, and that's it. Right. Of course, actually getting into to solve all this equation in more complicated geometry is harder, right? But essentially, you just need these 5 equations to solve all of, figure out basically all of like, all of electronics, all of electrical systems, most of the motion in the atmosphere, 99% of chemistry, because there is some quantum mechanics in chemistry, right? Um, so all of that can be solved just with these 5 equations, which is really nice. Okay. All right. Just to give you guys a little bit further, there's more version of this where, for example, this equation that's this lady is wearing also has 4 different equations. Well, actually, 4, yeah, there's 5 terms in this equation that actually tells you not only about electricity and magnetism, but it also tells you about like nuclear reactions and what is actually inside a proton, meaning like what's actually making up the nucleus and the proton itself. This is known as the standard model, and you can actually, using this single, it looks very simple, but there's a lot of complicated math in it. But using this simple equation, you can actually derive everything else inside the nucleus, including like atomic physics and stuff like that. And this guy Einstein also came up with something that this equation, the Einstein field equation, that describe all of gravity also. So gravity is right now a separate thing. But there's still like a lot of unanswered questions in physics or in science, this stuff called dark matter, this stuff called dark energy. Why is our universe expanding? I myself spent 6 years of my life looking for this thing called minimal supersymmetric model, where it's supposed to kind of merge the electricity, the nuclear reactions, and the strong force into a single theory, and it turns out not to exist. Okay, because right now these different theories has different behavior when you go to very high energy, and they don't cross in a single point. And when I was, a silly undergraduate going into grad school, I thought that, if we have this, right, all this math will turn out to be really great and it'll merge in a single point, but it didn't happen for me. Okay. But you should still, people should, everyone should still trying to figure out what the universe is about. Okay. So if you're interested in any of this stuff, come talk to me during office hours or after class. Okay. So still got, we only have like 17 minutes. Okay. So what's next? We're going to talk about what the effect of Maxwell's equation actually is. Okay. From these 4 equations, so this section 31.5 is known as advanced topic. It means there's actually math in it that we don't expect you to know. So I'm just going to kind of conceptually talk through it. I didn't assign any homework, and there's nothing going to be on the test on this. But it is important for you to see this before we actually write down what describes electromagnetic waves. Okay. So these 4 equations that we have, okay, are the Maxwell's equation. Okay. In fact, right, there's this little thing here. This used to be Qn over epsilon naught, right? We're going to be in a system where there's no charges around. So there's no net charge, okay? You don't even need a charge to generate light, okay? That's kind of the cool thing about it, okay? So what happened is that what you should think about when you see these equations is that, well, somehow a changing magnetic field gives you electric field, right? So therefore, a changing magnetic field creates a electric field, right? But then that means the electric field is changing, right? Right? So that causes the electric field to change. But when you have a changing electric field, it causes a magnetic field to change. So you're in this kind of circular loop here, like it's just kind of a trap for these fields that they have to exist as soon as they get created, right? They will propagate actually forever until they, hit some sort of matter and charge or stuff like that. Okay? So these are known as self-sustaining fields. Okay? Okay. And what this looks like for electromagnetic field case is like this. So let's say if you think about the red as electric fields and the blue as magnetic fields, okay? If you have some electric field that's decreasing over time, right, that will actually generate magnetic field, okay? And for our case of electromagnetic for light, they're actually perpendicular to each other. So whenever the electric field is changing, it's getting smaller and smaller and smaller, it also changes the magnetic field, okay? But the changing magnetic field also creates electric fields, so the two are kind of like coupled together, okay? And if you feel like it and you want to do the differential equation stuff, you can read through about 2 pages of math. And what happened is that you will actually derive this thing called the wave equation for electromagnetic field, which is a second order differential equation with time and space. Okay, you can actually do this in all 4 dimensions if you want, but we're not going to talk too much about that. But we're going to observe some interesting thing about this. Okay. Okay. First of all, right, these constant epsilon naught and mu naught are in the equation, right? Remember that the speed of light is actually going to be 1 over square root of epsilon naught times mu naught, right? So if you square this, right, this will actually be epsilon naught mu naught, okay? So this factor here, right, actually is the same thing as the speed of light squared, right? So just having electric field that exert a certain forces on charges, right, and a magnetic field that's moving, and that electric charge, a charge that's moving in the magnetic field, and and how big that force is, right? Magnetic force and electric force, right? That's what those constants are about, right? How much of a force does electric field cause? How much of a force the magnetic field cause, right? That tells you exactly how fast light has to travel. Okay. Okay. So let's just go back. So therefore, if you actually take this number and square root it, multiply them together and square root it, you actually get about 2 point. Well, it's actually the book rounded up. It's actually like 2.9998, but rounded to 3 sig figs is 3.0 times 10 to the 8. So in any of the homework you should be able to just use 3 times 10 to the 8, and that's the speed of light. Okay. Okay. And the speed of light is in vacuum. Okay. Be a little careful. Next chapter, we're going to deal with things that are not in vacuum. So if you are not in, you're in space, that's how fast light will be. Okay. In air, it's approximately that. It's actually different by 5 1,000ths, 5 10,000ths. So 0.04%. Okay. It's a tiny difference. Okay. But that's going to be significant when we start talking about this stuff. Okay. But this comes out to be kind of interesting. We're not going to try to solve it, but we'll just tell you what the answer is. If we were to solve this second order differential equation, what we'll end up with, one of the solution is actually known as the plane wave solution, where you can describe the electric field, and we'll just point the electric field in the y direction. Okay, it doesn't have to be, but we can orient our coordinate system such that happens, where the electric field is oscillating up and down, up and down, up and down like this, just like a wave. Okay, and the magnetic field is going to oscillate in and out, in and out, in and out of the board, okay, along the z direction. Okay, this wave actually propagates forward in the x direction at the speed of light. Okay, and that's what this complicated equation up here is describing. Okay, so there's some sine waves. So since they're both sine waves, they're going to start off at the origin at 0, 0, because sine starts at 0, right? And it's going to oscillate up and down. And it's going to be there's going to be two dependent variables in here. Okay, not just one, right? This is what happens when we have waves. Is that sine of kx? Remember, this k is known as the wave number. Maybe not remember, but we'll play around with it. Okay, omega is the same omega, the angular frequency we've been playing around with, and then times time. Okay, if you want to convert this to wavelengths and frequency, there's this the equivalent there, but usually it's easiest to work with these because then you don't have a bunch of 2 pi's going around everywhere, right? Okay. All right, and this is how you can describe electromagnetic wave. By just basically writing one equation for the electric field and then one equation for the magnetic fields. Okay. They look very similar, right? But they have different amplitudes, right? Be a little careful, okay? They don't necessarily have to have the same amplitude. All right, chat? The wavelength is changing. The wavelengths are staying the same, right? Because they both have the same wave numbers. Well, it only propagates along, well, we're going to set up the coordinate system so it propagates along the positive x direction, so there's no, so if you want the wave to propagate along the z direction, you would just write the same equation where we replace x with z, right? Right. Okay. Okay. So let's look at some properties. So this is, you chatting about what we're going to talk about anyway. Okay. So one of the things is that these are transverse wave. Does anyone remember what the other version of wave is besides transverse wave? Longitudinal wave, right? Transverse waves are the ones that goes up and down perpendicular to the direction of propagation. Longitudinal wave is the one that goes along the direction. So sound wave is a longitudinal wave. Light is a transverse wave. Okay, so that's one of the properties of electromagnetic wave. the other one is that what happened is that the propagation, meaning the direction that the wave actually travels, is perpendicular to both the electric field and the magnetic field, right? If you go up here, right, the wave is propagating this way, but the electric field is along the y-axis, the magnetic field is along the z-axis, the wave actually goes along the x. They're perpendicular to both of them, okay? And we can use this to write another quantity called the pointing vector. It's actually not because it points in the direction of, well, you can remember it as that it points in the direction of the wave, but it's actually named after some Dutch guy. His name is Pointing, okay? So this is known as the pointing vector, right? And it's defined as just the cross product between the electric field and the magnetic field. So if you do the way that I do my fingers is that the first vector, right, cross with the second vector, right, gives you the direction of the third vector, right? So it's going to go along this direction, okay? Right? And with this, what we can do is that there's actually a relationship between the electric field strength, actually this should be E naught, B naught, okay? The electric field strength is bigger than the magnetic field strength by a factor of C, okay? So this is why electric field tends to be, so if you guys calculate electric fields, right, in like homework and stuff like that, they turn out to be like 10,000, 20,000, 30,000, right? Where magnetic field is like, oh, 1 Tesla is a big magnetic field, right? That's because of this factor of the speed of light, which is 3 times 10 to the 8. So whatever the magnetic field strength is going to get multiplied by basically 3 times 10 to the 8 to give you the electric field in the same wave. Okay, and that's how the magnitude of these waves are, sorry, the amplitude of these waves are related to each other. Okay, so always remember that electric fields are big, magnetic fields are small, so therefore you want to multiply the magnetic field by the speed of light to get a big electric field, right? That's how you remember that stuff. Okay, all right. So let's do got 5 minutes. Let's do a poll, or just, raise of hand. Right, let's say we have a electromagnetic wave traveling in the positive y direction, so the wave is actually traveling in this direction, right? Which direction, and if the direction of the electric field is this way, what is the direction of the magnetic fields? Okay, so we can figure this out. Which is it? How many of you guys think is A in the positive x direction? Okay. All right, most of you, and I think that's right. Let me just double check, right? So if I do my one finger, right, I don't know where the second finger actually goes, but I know where my thumb has to go, right? So it has to be in this direction, right? So it's actually, the magnetic field's actually in this direction, okay? Or in the positive x, okay? So hopefully that makes sense, okay? So the magnitude of the pointing vector, you can actually calculate what that is, because it's basically the product of the electric field times the magnetic field divided by this mu naught thing, right? Because it was just defined up here, right? Because if we know that these two vectors are perpendicular to each other, right? So sine of 90 degrees gives you a factor of 1, right? So therefore, if you want just the magnitude, is the magnitude of the two vectors times the sine of 90 degrees divided by mu naught. But we know that, right, the magnetic field is actually equal to the electric field divided by the speed of light, right? That came from up here, right? Okay, so we can actually replace the magnetic field here, right? And then you end up with E squared over C divided by mu naught. But then, once again, we're playing around with these algebra, where we know that C squared is actually equal to 1 over mu naught epsilon naught, okay? So therefore, right, if I pull one factor of C's down here and one factor of this epsilon naught up here, we get epsilon naught C equal to 1 over C mu naught, and that's what I'm going to exactly replace to calculate what the Poynting vector magnitude is. It's just C times the electric constant times the electric field square, okay? So one thing to also note about electromagnetic wave is basically this Poynting vector thing, okay, that we're gonna play around with, right, is proportional to the electric field square, or it could be proportional to the magnetic field square, right? But usually we calculate electric field because this is just a lot easier to measure electric field compared to magnetic fields, okay? All right, still got 3 minutes. So let's talk about how we can use this Poynting vector to calculate power and intensity, okay? Right, the Poynting vector, this quantity up here, well, actually the magnitude of the Poynting vector, right, if we take the average of that, we actually get the intensity, okay? This I is not, doesn't stand for current, this stands for intensity of the light, okay? Remember when we did sound waves, right? We figured out that intensity as the sound travel further and further away from me, right? The intensity goes down as 1 over r squared, right? So therefore, the average of the Poynting vector, right? The time average of the Poynting vector is exactly what the intensity is. But when you take a time average, what happened is that instead of the same magnitude, right, you basically decrease it by a factor of 1/2. Because remember when we talked about this, when we did AC circuit, is that if you have an oscillating circuit like this, and the amount of, if you want to take the average power of it, is actually 1/2 whatever the amplitude is, right? So that's what this 1/2 comes from down here, okay? So just be a little careful. The magnitude of the Poynting vector is E squared times C epsilon naught. But then if you want intensity, which is usually what you want to use most, right, there's an extra factor of 1/2, okay? Yeah, and then as I mentioned, the extra factor 1/2 comes from just averaging over the sine square function, okay? Last thing I'll talk about today is also how, just like what we did with sound waves, right, the intensity of a wave drops off as 1 over r squared. So this is the inverse square law, once again, squared law, right? You can imagine you have some source of light, sound, ocean waves, whatever it is, whatever wave you want to talk about, right? As this wave spreads out, it gets less and less intense as it spreads out to a larger surface of a sphere, okay? And therefore, right, whatever the intensity is, right, it's going to be equal to the amount of power that's created at the source divided by the surface area of a sphere, right? 4 pi r squared, okay? All right. So let me just wrap up today. Do I have time to do a quick example? Maybe 1 minute over? No, because this is right there, right? So let's just wrap up with this quick example. So let's say we have some digital cell phone that broadcasts at 0.6 watt per of power, right, at some frequency of 1.9 gigahertz, okay? We want to find the amplitude of the electric field and the magnetic field at 10 centimeter away from the user's brain. So I'm going to have this phone, right, it's broadcasting some amount of power, energy out of here, right, and want to figure out what is how much is it affecting my brain, basically, okay? So remember that the intensity, right, goes down as the amount of power, right, over 4 over 4 pi r squared, where r in this case is this 0.1 centimeter, so that's 0.1 watt divided by 4 pi, and this has 0.1, right, converted to meters, okay? If we calculate what that is, 0.6 divided by 4 times pi divided by 0.1 square. Oops, screwed up. Okay, so this has an intensity of 4.7, well, 8, and this is going to have units of watts per meter square, okay? And remember, this is equal to the pointing vector average, right, which is actually equal to C times epsilon naught times the electric field strength over 2. Okay, so now we can actually solve this for the electric field. Okay, so this is 2 times 4.78, right, and then divided by the speed of light and then epsilon naught. Okay, so speed of light is just 3 times 10 to the 8, and epsilon naught, that one actually hopefully remembers 8.85 times 10 to the minus 12, right? Okay, times 2 divided by, ooh, but then all square rooted, right? Because there's the square here. Okay, divided by 3e8 divided by 8.85 e negative 12, all square rooted. Okay, so the electric field is actually about 60 volts per meter, okay, in your brain if you're holding your cell phone up next to your head. Okay, so any idea how to convert this to magnetic field if we know the electric field? You're right, divided by the speed of light, and that's it. Okay, I'll let you guys do that. Okay, all right, does that make sense? Okay, so you're going to use intensity to calculate from the power, right? And then from that, you can actually calculate what the electric field is by using the pointing vector. Okay? Let's wrap up.